Okay, now you should be able to adjust the size of the screen, so you can make the PowerPoints bigger, or you can make me bigger, whichever the case may be. PowerPoints look pretty good, so I wonder if it's not my camera is the problem. Well, rather than eat up time trying to solve this technical problem, let's just go ahead. And if it turns out to be a really crappy production, I have previous recordings that are better quality than on this particular chapter. And if necessary, I can insert that discussion. Okay, chapter 3. This is the third and the last chapter for exam 1. We're going to talk about atomic structure in the periodic table. Those two ideas are intimately connected. The structure of the atom actually can be deduced from the structure of the periodic table. And I hope that becomes evident as we go. All right, we're going to look at, we're going to start with the atom. And the Greeks had it wrong. In fact, John Dalton had it wrong. Calling it an atom means that you can't cut it. It means you can't reduce it any further. It's just a black ball. Excuse me, a black ball. But we now know that the atom is has subatomic particles, and the number and arrangement of those particles determines chemical behavior. So we're sort of forced to go that way. Rather than stop here for too long, let's just move on. Okay, I found this flyer. I get a lot of these from this particular website, Compound Interest. They got a lot of information in a compact form, and this just shows the progression of the structure of the atom from early 19th century with John Dalton up through J.J. Thomson, discovery of the electron, and then Ernst Rutherford and his nuclear model, and Niels Bohr created a planetary model, and plus other things. And then finally with Erwin Schrödinger and his wave equations actually got closer to reality. How is the atom really structured, and how are the electrons, why do they behave the way they do in that space around the atom? So we've got three particles that are, for us anyway, are essential to the structure of the atom. Actually, there are subatomic particles, but I'm going to leave that discussion to nuclear physics. If you have a hankering to go that route, then more power to you later in your career. The electron is the negatively charged part of the atom, and the electrons reside outside in the outer space of the atom. So the electrons are going to be out here somewhere. Protons are the positively charged part of the atom, and they reside in a central nucleus. Since I've got three here, I'm going to put three in the middle. Okay, so this is the nucleus. And that is where most of the mass of the atom resides, in the nucleus, which means that the protons are very heavy by comparison to the electron. In fact, the proton is about approximately equal to 1,800 times the mass of the electron. So even though they have equal charges, they don't have equal masses. Now, what was also discovered was that the protons did not account for all of the mass that's contained in the atom. So once Rutherford's model of the nuclear model for the atom was widely accepted, in fact, before then, he set a graduate student and later research associate, Chadwick, to discovering what that particle was. It had to be neutral, because with the proton and electron, the neutrality of the atom had been established. The balanced number of electrons and protons made the atom neutral, so we can't have another charged particle in the nucleus. So Chadwick, over time, discovered and proved that there was another particle in the nucleus called the neutron. And for this particular, this would be lithium, actually. And I think lithium is going to have, let me check myself. The most common, I'm going to use a term we haven't defined yet, isotope of lithium would have actually 4 neutrons. Okay, and these are also inside the nucleus. So the nucleus is where most of the mass resides in the electron. But the electrons, just because they don't have mass, doesn't mean they're not important. Because when you consider chemical reactions, when 2 atoms come together and they're going to do something, what do they see first? They see electrons first. They don't see the nucleus. They can't get close enough. The nuclei can't get close enough because it's positively charged. So there's repulsion. But there's also repulsion between the electrons of one atom and the other. So what happens is, to make a long story short, you get attraction between the protons of one atom and the electrons of the other, which draws them together. And then the interaction between the electrons is where the chemistry happens. Okay, so the exact amount is 1,837 times. The neutron is about the same size as the proton, but it's a little bit heavier. And if we had time to go into, pardon me. Hello? Oh. Junk call, sorry. If we had time to go into the subatomic structure of the nucleus and the concept of nuclear decay, we'd find out that that extra mass in the neutron contributes to radioactive particles that emanate from the atoms under certain conditions of decay. So that's all I can say about that in just a few seconds. There's a reason for that difference in mass. Okay, so I described the nucleus just a second ago. Small, dense, positively charged protons and neutrons. The atom is neutral. And it's neutral because the number of protons equals the number of electrons. Now, that doesn't mean we can't form charged atoms, which we call ions, but this is our starting place, the neutral atom. And then we produce charged particles or ions by the change in ratio between the protons and electrons. Okay, subatomic particles of an atom, protons, neutrons, electrons. That's a no-brainer by now. Okay, so, yeah, that's not behaving. That's going to create a problem. Okay, when we write the symbol for an element, and I don't think we've even talked about that yet. Let's just, for argument's sake, say we're going to represent the atom with a symbol, either one letter or two letters. I'm going to use an X to represent that atom. There are four positions, four corners to this symbol that are reserved for certain information. And let's see. There it is. Okay, there's our symbol, and I'm using an X. Down here is how many of them are there? Right? If you have, if you need to represent an atom, an element, a compound with a certain number of these atoms, then you put the number of atoms down here as a subscript to the right. If the atom is charged, then you represent that in the upper right-hand corner. So this is where the charge goes. Now, if you feel the need, you can put a 0 there for zero charge. Under certain circumstances, that's useful. But in chemistry, usually, if it doesn't have a charge, we don't put anything. If it does have a charge, then we'll say how many there are. Let's say we have an atom that has a 2+ charge. Well, what does that mean? That means you've got 2 more protons than you do electrons. There's an excess of 2 protons. Down in this corner is the atomic number. And the atomic number equals the number of protons. That is a unique number for every element. So if you have a different number of protons, you have a different element. Hydrogen has 1 proton. Helium has 2 protons. If I say, I'm thinking of an element that has 3 protons, you instantly know that's lithium. Or if I say, I have lithium, how many protons do I have? You know it's 3, right? They're joined at the hip. So the reason I emphasize that is when you form an ion by adding or subtracting electrons. If you change the number of protons, you have a different element. Okay? So it's always with add, subtract electrons to get an ion. Okay, and up here, this space is reserved for the mass number. And the mass number is the summation the number of neutrons plus the number of protons for that atom. So in the previous example, we had 3 down here, and this was 4. So the mass number for lithium would be 7. The mass number is always a whole number because it's the summation of 2 whole numbers, the number of protons, the number of neutrons. That's not to be confused with the atomic mass. Mass number and atomic mass are 2 different concepts. They're related in some respects, but they mean different things. This is always a whole number. And it can change. If you have an element with so many protons, but you have so many neutrons, then you'll have a mass number. But if you add or subtract a neutron, you'll still have the same element. You'll just have different mass number. Okay, and this is like any equation, right? If you say the mass number is equal to the number of protons plus the number of neutrons, then it's like any algebraic expression. If you know two of those, you can solve for the third one. If we know this one and that one, we can say how many protons we have. If we know this one and that one, this one and that one, we can say how many neutrons there are. Or if you know these two, you can find the mass number. Okay. I'll leave that there for a second in case we need it. Here's an example. Sodium. Na is sodium. Right? It's derived from the Latin word natrum, which means sodium. So what do we have here? Well, sodium has 11 protons. And if you know 11 protons, you know it's sodium. But in this case, how many neutrons do we have? We have 12 neutrons. Okay, now I've been using some terms here because I had no other choice. And now we want to be sure that we have an agreed upon standard definition for these terms that I've been using. An element is a pure substance. In other words, it cannot be reduced any further by either physical or chemical means. It's as simple as you can get. And now we know the reason that that element cannot be reduced any further by chemical means, because elements are composed of individual atoms of the same kind. Every atom in a chunk of element is identical chemically. So that makes it a pure substance. Right? Their chemical identity, their properties are fixed. Okay, just to review, number of protons, number of electrons in a neutral atom is, well, let's see. Yes, that's true. The atomic number of an atom is equal to the number of protons and the number of electrons if the atom is neutral. If it's neutral, then those two values are equal in magnitude. Now we come to the concept of isotopes. I used that word earlier. Now I need to be sure and define it. An isotope is an atom of an element that has a different number of neutrons than its neighbor. So we could have lithium, which has 3 protons. And in our previous example, the mass number would be 7 because it has 4 neutrons. But there are a very small number of lithium atoms in nature that only have 3 neutrons. So that's the way we would represent that isotope. Now, I mentioned in nature. I think I'm safe in saying that all naturally occurring elements are a mixture of different isotopes. Some of them, most of them, in fact, the lion's share, the vast majority, are a single type of isotope. And then you have some others that are different numbers of neutrons. One exception is chlorine. Chlorine is almost 50-50, 2 different isotopes. And I'll explain what that significance is in just a few minutes. They have identical chemical properties, so they cannot be separated chemically. That's why it's still a pure substance. Even though the individual atoms have slight differences, their chemical properties are the same. Their physical properties are a little bit different. simply because they have different masses. So when we separate isotopes, when we need to determine what is the percentage of the mixture of different isotopes, we use physical means of separating. And the most common way is called a mass spectrometer. It separates based upon the mass of individual atoms. And I'm not sure if I have a slide. If I don't, then I'll talk about it in a minute. Now, the only way that you can get, well, there are two ways that you can get a single isotope of an element gathered together in one place. You can use the mass spectrometer, and when it separates those isotopes, you collect them. And then you can have pure single isotope of that one element. The other way is to make them. And the man-made elements can be made usually in a nuclear reactor by bombarding other elements with neutrons. And then they go through a decay process and they produce different elements. Under those circumstances, you would still have to separate them, of course, but that way you could manufacture isotopes. All right. Here's another example, silicon. Right? We know it's silicon because it has 14 protons right here. Oops, sorry. But it has different number of neutrons because the mass number is different. That's the clue. The mass number is different. It's a different isotope. And we can calculate the number of neutrons. We just subtract 14 from 28 and we get 14 neutrons for this isotope. And we subtract 14 from 29 and get 15 neutrons for this isotope. I think everybody nowadays has heard of heavy water. Heavy water is the same chemical formula as normal water. Right? 2 hydrogens and 1 oxygen. It's heavy because the hydrogen is, right, 1 proton, but it has, instead of most hydrogen is no neutrons, mass number 1. But heavy water has added a neutron. So now it has a mass number of 2. I won't go into the significance of heavy water right now. That's readily available information. Okay. So a certain isotope X has 23 protons and 28 neutrons. What's the mass number? Well, 23 plus 28 is 51. Okay, we know that. That's easy. What's the element? Well, you need your periodic table now. So if you get your, let's see. I should have pulled one up. Keep one handy. Periodic table. Hold on a second. Let me see if I've got one in this book. Here we go. Okay, so this periodic table is arranged, there we go, pull it back a little bit, is arranged from upper left to lower right, increasing atomic numbers. Also increasing masses, but we're not going to get into that right now. So all you have to do is go from left to right, top to bottom, and keep following along until you find 23. And 23 will be a prominent number, located in different places depending on who created the chart. But we find that 23 is vanadium, okay, with a symbol of V. So if we write vanadium, with all this information included, then we would have 23 and 51. And it's neutral, and there's only one of them, right? So in chemistry, if there's only one of them, we don't put the 1 there. And if there's no charge, we typically don't put a charge. We don't put a 0 there either. So in chemistry, very often, most of the time, we're not interested in either one of these, because if you have the symbol, you know how many protons there are. So when we write the element or compounds, combinations of elements, we usually just use the symbol, and then any subscript that tells us how many of the atoms there are. Okay, now the difference between mass number and atomic mass. Right. So mass number, I'll just, as a reminder, I'll write up here, mass number equals the number of protons plus the number of neutrons. Okay. Atomic mass is a weighted average of isotope masses. Okay, so we need to know the individual masses of the isotopes, and then their relative abundance. The reason, and this example, I don't want it to confuse you, because the only atomic mass for an isotope in this group of 3 carbon isotopes that is a whole number is carbon 12. So this one has a mass number of 12, but by convention, by agreement of the scientific community, this is our standard. That carbon isotope also has an atomic mass of 12 atomic mass units. I think my marker's getting weak, so I need to get a, let's see, hold on a second. There we go. All right. Not cooperating. Yep, I'm gonna have to let it sit upside down for a few minutes and muddle through with this other one. Okay. So that's what this statement at the bottom of the slide is. One atom of carbon 12 is the prose form, weighs exactly 12 atomic mass units. 12.000000. That's by agreement and convention. That's our established, that's our anchor point. Everything else is compared to this isotope. So none of the other isotopes of any of the elements, carbon or any of the other elements, their atomic masses will not be whole numbers. Now the mass number, yes, will be a whole number, simply because it's the summation of this whole number of protons and whole number of neutrons. But the atomic mass for that isotope in this unit of measure, the atomic mass unit, is will not be a whole number. It will be a fractional number. So the reason I brought that up was that we're using this example of carbon and its three most common isotopes to use this definition, weighted average. And this carbon 13 is not really 13, because 12 is the only one that's exactly 12. So 13 is going to be a fraction in real life. 14 will be a fraction in real life. But we're going to use those as if they were true values of atomic mass for those isotopes, just for argument's sake. If I were in the business of establishing very accurate values of atomic masses, then I would need the true value for carbon 13 and carbon 14. That being said, let's move on and use those values to determine the atomic mass for the naturally occurring mixture of carbon isotopes. So what we need to do is we need to say, what contribution does this isotope have to the whole? It's kind of like calculating your GPA, your grade point average, right? A class that is worth 4 credit hours is worth a whole lot more than a 1 credit hour course. So if you get an A in a 4 credit course, that carries a whole lot more weight than say you get a C in a 1 credit, you have to average them together. You're still going to be pretty well off. It's a weighted average. So let's see, does the next slide carry me through? Yes. Okay, so the average atomic mass for carbon, and we're going to use just the first 2 isotopes for obvious reasons. Carbon 14 is less than 100%. So if we use the first 2, then we're accounting for most of the mass, the atomic mass for the naturally occurring carbon. So that's why we only have 2 calculations in here in this summation. All right, 98.89% is 12 AMUs. Oh, I just noticed we actually do have the atomic mass units for carbon 13. That's good. The next trick is to recognize that percent means nothing. Percent is a dimensionless number. What we need is the fractional amount of contribution. So that's why this 98.89 has been changed to 0.9889. That's the fraction of the whole. So our whole sample is composed of 0.9889, 12 AMUs, and 0.0111 of 13.0034 AMUs. And if you do that math, take this fraction times that amount and this fraction times that amount, add them together, you get a weighted average of 12.01 atomic mass units for naturally occurring carbon. Now, are you going to find a single isotope with this atomic mass unit attached to it? No. It's a weighted average of a group of atoms. So this will not, this is not applicable to a single atom, but it is useful when you're talking about naturally occurring carbon, because now we have a value that we can assign to on average amount to all of the atoms in this natural sample. And that's the value it is to chemists, because chemists don't have time to separate isotopes and then do their chemistry so that they know the exact mass of each of the atoms. We're going to use naturally occurring carbon, or naturally occurring oxygen, or naturally occurring zinc, whatever the case may be. And using our periodic table, we will be able to find out what that value is for the natural abundance of that particular element in nature. And well, that's redundant. Natural abundance in nature. So that's the reason we do this calculation. And our periodic table has that information. Let's see. That's an example down here. All right. So if you look at one of these, you'll see in this case, at the bottom of that square is a value. That's a decimal fraction. And it looks like it's pretty close to the mass number for one of the isotopes of that element. But it's not exactly the same. And the reason is, I just showed you here, is that it is a weighted average of the naturally occurring abundance of isotopes. Now, I mentioned chlorine earlier. The value for chlorine is about 35.5. So if naturally occurring chlorine, which is 17 here, is 35.5, then this one, it probably has about half of this one and about half of this one. So if it's half this one and half this one, it's going to be right in the middle, isn't it? Okay. Most are not like that. Chlorine is an exception. These two apparently are very stable, and for some reason over Earth's history, we've accumulated an almost equal amount of each of those isotopes. All right. So stop me anytime if you have questions. Let's see. Okay, so for this exercise, say we have an element and we've determined using our mass spectrometer. In fact, let me show you how that works. A mass spectrometer will take a purified element with all of its isotopes. And the sample will go through a, let's see, it'll go through, it'll be bombarded, usually with electrons. And what that does is it ionizes all of the atoms in that element. I don't know if it's negative. Let me erase that. That may not be true. But what we do is we produce ions, usually positively charged. Okay, now that we have ions, we have a handle, right? Neutral atoms have got nothing to grab onto. So if we have an ion, we can grab onto it with an electric field and accelerate it under high voltage. So we accelerate these ions, and now this is definitely negatively charged. And we accelerate those ions through that electric field. And then we produce a narrow beam. So that's a process called collimation. And what we have is two slits, right? They're accelerating. If it goes through one slit, then they could come in from an angle and spread out. But if we have two slits perfectly aligned, the only ones that get through there are the ones that are going straight. So now we have a straight beam of ions. Now what you do is pass them through a magnetic field. And ions moving through a magnetic field will bend. Right? So we have a big horseshoe magnet here. Lack of a better term. And we have detectors over here. So we bend. Let's say we bend toward the field. So we bend that way, that way, that way. The ones that bend the most, since they're the same charge, then they feel the same force as they move through that magnetic field. But the bigger ones don't respond the same way as the smaller ions do. So the heavier ions don't bend as much, and the lighter ions bend more. Okay, so now you're separating based upon physical property, mass. So we have detectors out here that will pick up, or actually we can change the strength of the magnetic field, and then we have one detector. And as we scan the magnetic field, we just scan the abundance of the isotopes at the same time. Okay, so that in a nutshell is the mass spectrometer. And by using that device for this problem, we've determined that 62.60% of an isotope has a mass of 186.956 atomic mass units. And 37.4% of that same element are isotopes with a mass of 84.956 atomic mass units. Okay? So now we just go through that same calculation. We change those percent values to fractionals, so we can multiply them by the mass, atomic masses of the individual isotopes, then add them together for our weighted average. And when we do that, we find that we get a weighted average of 186.207 atomic mass units as an average, a weighted average for that element. All right. The question here, the next question in blue lettering is, what element is it? Well, we weren't given the number of protons. All right. So are we stuck? Maybe time to think. No, we're not stuck. I mentioned it a little earlier. The periodic table is organized top to bottom, left to right, increasing atomic number. The fact of the matter is that it also is increasing atomic mass, top to bottom, left to right. Now, there are a couple of places where you get atomic masses switched, right? So it's not perfect. And sometimes neighbors are very close together because of their mix of isotopes. But you're usually able to look for the atomic mass in the periodic table and identify the element. If you have a tie, if your calculations put you very close to two neighbors, then you need some other way to differentiate. But most of the time you can tell. Say 186.207. So if we look on our periodic table, which I got one right here, I follow down and keep following along till I get to 186. Let me see. I keep going, keep going. Here we are. In fact, it's this element. I didn't have you memorize that one. It's called rhenium. And it has an atomic number of 75. So it's pretty heavy. It's not as heavy as lead, but it's pretty heavy. And that value cannot be associated with any of the other elements. So it doesn't have any close seconds that can cause you trouble in identifying. So we know it's rhenium. Okay. Atoms of an element that contain different number of neutrons, just to check, that's isotopes. All right. So let's talk about the periodic law. The periodic law was used to construct the first periodic table. And that's attributed to a Russian. I'm gonna have to clean this thing off. It's bugging me. Give me just a second. All right. Let's pick up. If you're wondering what that stuff is, that's glugon. It works great. Trouble is, it leaves a residue that makes erasure beyond that difficult. So what I do, I still have some. I use WD-40. And that replaces that residue with something that's a little friendlier to my markers. I hope it works. It probably won't work and make a liar out of me. And you don't want to leave, you want to leave just a little film. You don't want to leave a lot. Okay. All right. So let's give it a try. Periodic law. Remember what we said about laws? Laws just say this is what happens under these circumstances. It doesn't explain why. Fortunately, once the periodic law has been invoked to build the periodic table, we find that it leads with gathering information over the years. It leads to information that can predict, that does help us with, it doesn't actually build the model of the atom, but it helps us to understand and deduce the structure of the atom from the table. So this is the first step, the periodic law. What it does is it arranges the atoms in a tabular form, the elements that is, by increasing atomic number. And it also positions those atomic number, the elements, in such a way that they agree, that those in the vertical, in the columns, agree with their chemical behavior. They're called groups. We used to call them families. Now we call them groups. But in order to get there, you need to understand the concept of the period. Okay, in physics, we have different types of motion. We have linear motion, starts here and keeps going until it stops. Or we have circular motion, goes around and around and around, and it goes around, starts here, it goes around, ends up here. That's called a type of periodic motion. It goes through a period, ends up at the same place. It's still moving. I mean, it did move, but it ends up at the same place. That's periodic motion. Another type of periodic motion is the pendulum, right? It swings, it moves, but it goes from here, over here, and then back to here. It's gone through one period of movement. So we use that concept with the periodic table, because the periodic table goes from left to right, increasing atomic number and atomic mass. And we keep lining up elements that share chemical behavior. And then when we get down to one end past the noble gases, we find that the next one down here actually looks like ones in this group over here. So we go through one period, go back over here, start another period, so that we can keep these things lined up in their groups. That's the period. The period is in a row. Groups are in columns. Okay. Now, I mentioned that we gave credit to the Russian, Mendeleev. But scientific advancement never occurs just full-blown out of somebody's head. We advance by small steps. In other words, we stand on the shoulders of giants, so to speak, those who came before us. Now, sometimes those that came before us proved to be wrong. So in the sciences, nothing is ever settled. Settled science is a lie. They don't belong in the same phrase. Settled and science do not belong together. Science is constantly being questioned. That's the characteristic of science. You question previous results, and if they work, if the previous ideas solve current problems, then you keep them. If they don't, then you try to explain why they don't, because that helps you advance to the next level. But sometimes they're just worthless and you throw them out. Perfect example of that is the Enlightenment period idea called phlogiston. Right? You look it up. It starts with a PH. Phlogiston. With the atomic theory, the phlogiston theory was completely debunked. So it was thrown out, discarded. It's in the waste bin of history. But back to the development of the periodic table. This fellow Dobereiner, who was obviously a German, noticed similar behaviors of elements, and he grouped them into groups of threes. So these three elements behave alike, these three behave alike, call them triads. But that's as far as he went with it. He didn't go any farther. Then another German, Meyer, developed the concept of valency. Now we understand valencies have to do with the number of electrons in the atom that are available to react. In Meyer's day, it was more based upon a practical approach, the concept of valency. He was saying that these triads had similar behavior because they had something similar in them that he called valency. And he put the elements in a tabular form. But that's where it ended. He didn't go any further than that. Mendeleev took that concept the next step. He said that these relationships in these groups were arranged that way, certainly because they had this valency quality, but what he started to do was he predicted chemical and physical properties. And as he tried to position elements in groups with similar properties, as they increased in mass, then he noticed that there were places here where if he put the next one in order, the next known element that was the next heaviest in order, it was in the wrong group. It didn't have the same chemical characteristics as the others in that group. So he said, well, look, the next group over from that is where it ought to be. And there's an empty spot right here. We haven't discovered that element yet. So not only that, he said, when you discover that element, and you will, it will have these properties, these physical and chemical properties. And he was right. We discovered elements to fill those spots. That's why Mendeleev is given credit for the periodic table, because he used it to predict the existence of as yet undiscovered elements. And these are examples: gallium, germanium, TC, technetium. Those places were empty in Mendeleev's chart. But in presenting and publishing this periodic table, publishing it, he also added the comments that these undiscovered elements would have certain characteristics and defined what they were. Now, at the time that Mendeleev put the periodic table together, all we knew was relative masses of the elements. We had no concept of atomic number at that time. It was up to a young physical chemist, Henry Moseley, he was an Englishman, who was interested in X-ray spectra of the various elements. So what he would do was he would energize the pure element in a device of his own making, and it would give off high energy X-rays. And he used a spectrometer to determine, after he calibrated it, what is the wavelength of that spectrum? Where is it located? And then he had a formula that was able to predict the spectral wavelength of each element. And the only thing that varied from one element to the next was this one number. And the number was always a whole number increment. 12, 13, 14, 15. Every time he changed that number, he got a new spectral wavelength that was directly measured for the next element. So the atomic number originally had nothing to do with protons. I mean, we didn't know it was protons that he was measuring. We just knew that it was this number that fit into his equation. Later on, that was associated with atomic number. Unfortunately, notice when this work was done in 1913. 1914, World War I came to Europe. And shortly thereafter, Henry Moseley volunteered and went off to fight for his country and died. So that was the end of his career. And that was a great loss, I should say. There's no telling what he could have accomplished had he gone, had he lived through the conflict. Okay. Now, in the periodic table, we've mentioned periods. Those are the rows, right? Hold on a second. I've got a periodic table right up here. I just need to reach it. Okay. Now, here we go. Is it big enough to see there? Yeah, it's big enough. I'll move it closer to the camera if I need. Okay, the rows are the periods, and the groups are vertical columns. Some of these groups have acquired names over the years. This first column, the one with lithium, sodium, potassium, rubidium, cesium, those are called alkali metals. And they're metals because they're on this side of the chart. Metals on this side, non-metals on that side. Now, I'll talk about that in a minute. This first column is alkali metals. The second column is called alkaline earths, or alkaline earth metals. If we move to the far side, we get noble gases. They are all gases, and they're noble, or they're often called noble or inert. Inert is more accurate, actually, because they don't react with anything, not voluntarily. And we're eventually going to see why that is. Then right next to the noble gases, that family, that group, is the halogens. Fluorine, chlorine, bromine, iodine. Those are all halogens, and they have similar behavior, just like all the groups. The next one over is the oxygen group. They're called calcagens. And that's kind of that's grandfathered in from alchemist days. The next group over, the nitrogen group, are called pnictogens. Starts with a P. All right, those are the only groups that we have vertical. Now there are a couple of partial periods that fit. Let's see, right here where that red line goes, right there, right in here. One fits in here, one fits in here. The upper one is called the lanthanides, simply because the first member of the group is lanthanum. The second one are the actinides, because its first member is actinium. And the reason they're put down here in separate rows is partially for convenience, because if you had to stick them in here where they belong, then it would expand your chart to unmanageable size. So we move them outside. And actually, I hope to show you that there's good reason from an atomic structure standpoint for putting them out here as separate members. Okay. Oh, here's a periodic table. Okay. So one thing you'll also notice about this periodic table is these groups also have numbers. They have names and they have numbers. One system of numbers is an older system. The one here, see, there's my cursor. The one here with the Roman numeral and A, 1A, Roman numeral 2A, over here 3, 4, 5, 6, 7, and 8A. And then down in here we have the B's. These are useful, and I'll have to explain why they're useful later. But the International Union of Pure and Applied Chemists, IUPAC, decided some years ago that we should actually number them sequentially from left to right. So we go 1, 2, 3, 4, 5, and we include all these what we call transition metals, transition elements. We follow those all the way across to 18. So when you're doing that extra credit exercise, 1 through 18 is the one I want. 1, 2, 3, 4. That's the one that's asked for, simply because it's the current version. And then the periods are numbered from hydrogen. Hydrogen and helium are in the first period. That's it. And there's good reason for that. I'll explain that. I hope to explain that later. And then the second period starts with lithium, and it goes lithium, beryllium, boron, and skips over. There are no transition elements in this group right here, in this period. This period has no transition elements either. You only get transition elements when you get to the fourth period. And there's reason for that on an atomic structure level. So what I'm saying is, if you know how the periodic table is arranged, you can write the electronic structure for any element. Okay, other divisions. I mentioned metals and nonmetals. Right? This heavy black line here, which goes underneath boron and then between aluminum, silicon, it stair steps down from there. To the right are the nonmetals. To the left are the metals, which means that most of the periodic table is classified as metals. And they have metallic characteristics, right? If they're polished, they have a luster. They're malleable. That is, they can be hammered into different shapes, or they can be stretched into long wires. That's called ductility. They also are generally good conductors of electricity and good conductors of heat. And all but one of them at room temperature is solid. Mercury is a liquid at room temperature. Gallium is only a liquid at just below body temperature. I think it's 35 degrees Celsius. So 37 degrees Celsius is body temperature. You put gallium in your hand and it'll melt. But at room temperature, it's a solid. Okay, all the nonmetals, they can be any one of those. They can be solid, liquid, or gas. And if they're solid, they're brittle. And they're kind of dull looking too. Okay, characteristics, let's see. All right. Let me go to the next slide. Elements arranged in the periodic table. Now, they're arranged according to increasing atomic number. It wasn't always that way, but now it is because we understand what atomic number means. Where Moseley got his X-rays, those X-rays were actually coming from the nucleus, where the protons are located. Okay. So I mentioned characteristics of metals: luster, conductivity, malleability. Those are metals. Nonmetals. What this statement actually says is the characteristic of nonmetals is they're not metals. They're absent the properties of metals. They can be any phase, and when they're solid, they're brittle. So these compare side by side, and this is taken straight out of your textbook, so you can look at that at your convenience. Here we show a blown up version where the dark line between metals and nonmetals is located. I'll also draw your attention to those elements that are very close to the line. In particular, silicon, germanium, arsenic, antimony, Sb, tellurium, and some authors include polonium. These are so close to that line on either side, sometimes they behave like metals, sometimes they behave like nonmetals. It depends on the reaction environment. And for that reason, we call them metalloids, because they're sort of like metals, but not completely. Okay. All of these are characteristic differences between metals and nonmetals. All right. Now, the structure of the atom. The structure of the atom, and actually the electronic structure of the atom, because remember what I said, when two atoms come together, the first thing they see is electrons. So if we know how the electrons are arranged in that space outside the atom, we have a clue as to how they're going to react with each other. So first we have to define what is that arrangement of electrons. Okay, so let me, I'm going to move that chart off for a minute because I need the space. Let me see if this thing's working now. It's getting there. Still not there. All right. Let's see if one of these might work. brown one. That's a little better. Okay. Now, to understand the structure, the electronic structure of an atom, we need equations. Remember that earlier slide, on the far right of that slide, we started off with John Dalton, and we ended up with Erwin Schrödinger. Schrödinger developed a set of equations, wave equations, that described the probability, one aspect of the equations described the probability of finding an electron in a particular space around an atom. And it was based upon 4 numbers. These 4 variables inserted into his equations would answer the question for individual electrons in the space around an atom. Those are derived from quantum mechanics, right? We're not going to go into quantum mechanics in detail for 2 reasons. It's too much. Plus, I'm not qualified. I can describe these 4 numbers and how to use them. That's where I'm fairly confident. Okay, the first one, your book calls the Electron Shell, and it's based upon N, the principal quantum number. N was developed by Niels Bohr. He was one of those names in that list in that previous slide in his planetary model. N is associated with the energy of the electron. And even in Schrödinger's equations, N is still designated as a descriptor for the energy of the electron. The way your book puts it is, in this region of space, any electron in that space will have approximately the same energy as any other electron. So if 2 electrons have the same principal quantum number, their energies are going to be very similar, with only very slight differences. And they will spend most of their time at that distance from the nucleus. So that dictates the size of the shell, that electron shell. Now here's a concept that we need to hammer into our heads. When we talk about energies of electrons, if this is the nucleus, and there's an electron out here, the closer the electron is to the nucleus, the lower its energy. So an electron, as it moves out away from the nucleus, it's acquiring more energy. Okay, until it reaches a distance of infinity. When it reaches that distance, now you have an ion, a positively charged ion. If we remove one of the electrons to infinity by adding energy, now you have an ion. Okay, so that's the concept for energy. Closer is lower energy. Okay. Now, this principal quantum number can have values starting with 1 and incrementing by whole numbers. So it can have 1, 2, 3, 4, 5, on up. Now, the next quantum number is called the angular momentum quantum number, or L. So this is energy. Angular momentum. Let's look at these as sublevels of each. So for each one of these, you can have individual sublevels of L's. So each one of these can have L's underneath them. So it's kind of like a branching system. So we have the 1, 2, 3, 4 ends here, and then each one of those can branch further into L's. Well, depending on what this number is, the L can only have certain values. And those values are N minus 1, incremented up to let's see, no, I'm sorry. Starts off at 0 and then incremented up to N minus 1. So let's say we have 3. We're at N equals 3. We could have possible L level sublevels, subshells they call it here, of 0, 1, and 2. N minus 3 minus 1 is 2. So that's the maximum. 0, 1, and 2. So 3 can have 3 L sublevels with 0, 1, and 2 as their numbers. 2 can have 0 and 1. That's it. Just 2 sublevels. 1 can only have 1, right? N minus 1. 1 minus 1 is 0. That's it. Okay? Now, what does the angular momentum mean? The angular momentum defines the let me see, I want to tell you right. I'm scratching my head. The angular momentum refers to the direction. Let's see. Is that right? No. This is shape. That's shape. Now, for convenience, if we have, let me leave that there. If we have 0, 1, 2, 3, 4 as our possible L numbers, we've assigned letters to each one of these. And I'll show you why that is in a few minutes. Zeros are S's, 1s are P's, 2s are D's, 3s are F's, 4s are G's, and you can go on up from there. But that's plenty. In fact, SPDF is all we're going to need. And what this tells you is not just the shape of the orbital, but the maximum number of electrons that the orbital can hold. Now, right now, you would just be memorizing those values. What I want to do is show you the rest of those numbers, and then these maximum number of electrons you can calculate yourself. Okay, I know I'm not going to finish on time because it's already 10:30. So the next one is the magnetic quantum number. Which is M sub L. And this is orientation in space. three-dimensional geometry of the orbital is based upon this number. This one is also derived from that one. So if this one can have several of these possibilities, then one of these possibilities could be expanded here, or another one could be expanded here. So we're expanding as we go down. This one is based on L and can be it can go from positive L, let's see, it can go from negative L to positive L by increments. So it can be minus L, it can be minus L. Let's take an example. Let's say it's 3. So we have 3 here, and that means we can have 0, 1, 2. So now let's take this one expands here. Let's take this one expand here. So 2 can be minus 2, minus 1, 0, plus 1, plus 2. Okay. So you can start with minus 2, minus this value, and go up, increment by 1, minus 2, minus 1, 0, plus 1, plus 2. 1 would be minus 1, 0, plus 1. And 0 would be 0. That's it. 4 would be, 4 could give you 0, 1, 2, and 3. So let's say we have 3 for our L. Then we could have minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Okay? Hello? Now we have one more. M sub S equals spin. The spin quantum number is simple. At each one of these magnetic M sub L's, say we had a plus 1. At each one of those, within that subshell, you can have a plus 1/2, a minus 1/2. That's it. That's the only possibility for spin, but it can occur for any one of these M sub L's. Okay? Now, this spin represents 1 electron. So if you put 2 electrons together, they have to have opposite spins. So you can have a minus 1/2 and a plus 1/2. Those 2 electrons can go into one of these M sub L's. All right. So as if your head's not spinning enough right now, let's look at the SPDF. These values here, 0, 1, 2, 3 are SPDF for the L numbers. So if you have an L number of S, right, how many of these can you have? Just 1, which means only 2 electrons in that one orbital. So for the S's, you can only have 2 electrons, maximum. Okay, for the P's, you have L equal 1. So that could be a minus 1, a 0, plus 1. And 2 electrons each for those, so that's 6 electrons. That's why you have 2 electrons here, 6 there. So let me back up. 2 electrons here, 6 there. For the D's are 2s, minus 2, minus 1, 0, plus 1, plus 2, 5. You have 5 subshells and 2 electrons each, which means 10 maximum. And we do the same thing for F. we have 7 orbitals with 2 electrons each. You have 14 electrons possible. Okay? All right. So when we talk about shape here, if it's an s orbital, it's going to be spherical. Okay. If it's a p orbital, it can be shaped kind of like a dumbbell. If it's a d orbital, it can be a crossed dumbbell, but actually the d orbitals have one other one that's not listed here. It's kind of a, call it a torus. It's a donut. And the f orbitals get even more complicated. These shapes are deduced from Schrodinger's equations. They're not observable. You don't actually see them. So this is an artist's representation of what they might look like. And these are actually probability spaces. In other words, this is where you're most likely to find the electrons, but they don't have to be there all the time. That's the thing about quantum mechanics. It's probability based. And there's another rule that's Heisenberg's uncertainty principle that says if you identify where something is this small, these electrons, then you can't know anything about their energy. If you know their energy, then you don't know where they are. Exactly. So this is a compromise between the two. We generally think they're in this region, this region, this region, this region, depending on their quantum numbers. All right. So when we get to M sub L orientation, the p orbitals might be dumbbells, but remember you can have 3 of them. -1, 0, +1, -1, 0, +1. And they're oriented differently in space. That's the M sub L character. And here's an explanation of the spin quantum number. We think of electrons as little gyroscopes. They can either spin this way or they can spin that way. Okay. Let's see. What is this? The space in which electrons move rapidly about a nucleus is divided into shells, subshells, and orbitals. That's their name for it. Shells, subshells, orbitals. Okay. Now we need some rules, because what we're going to do is, as you build an atom, you have to add, if you go from sequentially from one element to the next, you add a proton each time. When you add a proton, you add an electron. So we need rules to tell us where do those electrons go. All right. All right, let me see if this thing's working now. Getting better. Might be able to use it now. The first one is the Aufbau Principle. That's German. I don't know German, but I'm told that Aufbau basically means do it this way. And what that means is, practical terms, you add electrons as you build elements sequentially. As you add a proton and you add an electron, you put the electron into the next highest energy level. You start from the lowest possible energy level, close to the nucleus, and you gradually build out. That's the Aufbau principle. The second one is called Hund's rule. Hund's rule says as we add those electrons, if they're adding into a subshell at the same energy level, for instance, if N equals if N equals 2, then L could be 0, 1, or 2. Yeah, still not working right. Go back to this one. Okay. At these levels, if we say we want to go from here to our M sub L, right, expand that one. Okay, we have -1, 0, +1. Okay, this would be P, this would be S, this would be P, that would be D. So the P could have this one. And remember, the P orbitals are dumbbell shaped, so they could be in 3 dimensions. You can put 2 electrons in here, right? +1/2, -1/2 spin. 2 electrons can go in there. What Hund says is that you can't put 2 electrons paired together in here until you get at least 1 in each of these orbitals, right? Shell, subshell, orbital. So I like to draw a line here and line here and line here. And we have to put a spin up like that. We have to put a spin up and a spin up. Once you get those with each one in there, then you can go back, if you have to, and put the next one spin down. +1/2, -1/2. That's Hund's rule. And the last one is the Paulie exclusion principle. Basically what it says, in fact, this is the wording from your textbook. What it really says is no 2 electrons can have exactly the same set of 4 quantum numbers. In other words, if this electron has N equal 2, L equal 1, M sub L equals 0, then it can either have this one or that one. But it cannot have the same set of 4 quantum numbers. They're exclusive. One electron has its own set of numbers, and no other electron can have that same set of numbers. That's the Paulie exclusion principle. Seems like a no-brainer, but apparently scientists are simple-minded people. Believe me, simpler is better. So we actually state the rules. All right. The problem is, well, there are many problems, but when we start to build these atoms, what we notice is as you add protons to the nucleus and electrons to go with them, as you add more protons and more electrons, they start to interfere with one another. They start to modify energy levels. So at a certain point, the order of filling of electrons in these energy levels flips. So what you would normally think as an electron into a higher level should actually go into this level, and the next one should be out of order. Okay, that's not as daunting a problem as you might think, because we have a trick that will help us put electrons in the correct position. All right, this is an energy level diagram. That's the energy increasing on this side. These are orbitals. You don't have any trouble with the 1s orbital, right? 1 is the L, and no, 1 is the, excuse me, 1 is the N, and S is the L. See, that's why we use letters, because when we start to write the configuration out here, 1-1 would be kind of confusing. I mean, it would take just a slip of the finger and you'd write the wrong configuration. So that's why we give the L numbers. 0 is S, 1 is P, and 2 is D. And we don't have any F's here, but 3 is F. So that way we can write the configuration with less confusion. Okay, so this shows possible overlaps here, right? We would expect the 4s to be a higher energy than 3d. Why? Because 4 is energy, and it should be higher energy than 3. But as it turns out, with all that interaction going on, the 3d actually turns out to be a higher energy than 4s. Now, this is based upon mathematical calculation. Right? This is not observable, but it does explain chemical behavior, and that's why it has value. Okay, so here we go. This is the way you set up and independent of the periodic table, right? If you have a periodic table, then you don't need this thing. But if this is how it's developed. So we set up the possible orbitals, 1s, 2s, 2p. Remember, once you have 2, you can have 0 and 1, or s and p. If you have 3, you can have 0, 1, and 2, s, p, d. If you have 4, you can have S, P, D, and F, because you can have 0, 1, 2, 3. S, P, D, F. Now, we don't go into G's out here for good reason, because based upon the current set of known elements, we only need to go out to F's. G's aren't necessary, except if you're investigating movement of electrons into higher energy levels. Then you need to account for the highers. But for building the neutral atom, we don't need the G's. Okay, so what do? First of all, we write these. The 1's here, 2's there, 3's there, 4 there, like that. Just write them down. Then, to know how they fill, take a diagonal. A diagonal here. 1, then go back up top. 2s, go back up top. 2p, 3s, go back up top. 3p, 4s, don't go to 3d, right? That's why we have this diagonal, 3p, 4s. Then you can go back up to 3d, then to 4p, then to 5s, and you can go back up to 4d, 5p. So that is a way to actually list the orbitals in energy level. So if we were to write that out in a string all those together, we would start off with 1s, 2s, 2p, 3s, 3p, 4s, right? Then 3d, then 4p. So this is energy level from left to right increasing. Once you get that order, then you can start filling in electrons. And notice that here, you can only have 2 electrons in an s orbital. You can only have 2 there. How many can you have in P? Well, P can be -1, 0, +1. So you can have 6 there. So we could have 2 here, 6 there, 2 there, 6 there, 2 there. D's, how many in D's? Well, D's are 0, 1, 2. So we get -2, -1, 0, +1, +2. 2 each. 2 times 5 is 10. You can have 10 here, or you can have 6 there. So those are maximums, right? We will be limited to the actual number of electrons that were allowed for a given element. Say we had 10 protons and 10 electrons. We would go 2, 4, and 6 is 10. So we would stop there. That would be the electronic configuration for that neutral atom, just up to that point. Okay? Let's erase these because then I can use this thing again. Okay. Let's look at a practical example. Nitrogen. All right, so if we take a periodic table and we find nitrogen right here, how many protons does it have? We look over here, it says 7. It's got 7 protons. So nitrogen, 7, has 7 electrons. So the electronic configuration would be, according to the Aufbau principle, we go from lowest energy to highest energy. And then if necessary, we use Hund's rule. So nitrogen has 7. We used up 2 of them already. Use up 2 more. We've used up 4 so far. So how many we got left? 3 electrons. They have to go here. You can't go here until these are filled. Okay. So there are 3 there. Okay, how do they actually go into those orbitals? Right. Okay, remember this is -1, 0, +1. Sometimes they're listed as X, Y, and Z based upon their 3-dimensional orientation: X-axis, Y-axis, Z-axis. So we got 3. That means they go in like this, like this, like that. Okay? That's nitrogen. There we go. 2 in the 1s, 2 in the 2s, and 3 in the 2p. And this is the condensed notation for nitrogen. Now, most textbooks like this double barbed arrow with boxes. That takes too much time. I just draw a line and put a single barb, okay? Like that, like that, like that on the line. Then you can go back and put the other one the other direction if you need it. And this is the way they would look, right? You would have spin up, spin down, or +1/2, -1/2. Oh, okay, somebody's chatting. Oh, technical difficulties. Okay, I understand. I'll do like always. I'll process the video and so that you can go back and review it if you get kicked off of the of our meeting. And since we're Zooming everything, I'm going to record also the lab. Any discussions of the lab. Of course, we may run out of time if I'm as long-winded as usual. Okay, so we got spin up, spin down, +1/2, -1/2, +1/2, -1/2, then +1/2, +1/2, +1/2, and you're done. That's all your electrons. You've got nothing more to put in there. That's nitrogen, neutral nitrogen. While we're here, what would be nitrogen with a minus if we had a 1- charge on our nitrogen? That means you add 1 more electron, correct? where would it go? It would go right here, like that. If you had a 2 minus, you put another one here. Oops, wrong direction. There. What if it's 3 minus, which is the common charge for nitrogen in combination with a metal? You would put it here, like that. Okay? All right. Let's take another sample. Sulfur. Okay, let's make room for electrons. Here, here, here. All right. Now we need sulfur. How many protons? Well, we look at our periodic table and it's got 16. 16 protons, which means 16 electrons. So we can put 2 here, and 6 there. That's 10. We got 6 more to go. 2 here. Now we only got 4 more to go. 4 here. Okay? So that would be 1, 2, 3, 4. Like that. There we go. So that's as far as you go. That's the electronic configuration for neutral sulfur. How about barium? Well, before we go to barium, let me give you a shortened and abbreviated notation. Notice where sulfur is on the periodic table. Let's see, let me pull it up here. Sulfur is right here. Okay. Well, as we're building atoms, we can walk through, right? 1s1, 1s2, 1s2, 2s1, and you can just keep adding based upon this list. Okay. What if you get over here to neon, a noble gas? It doesn't react with anybody. What does neon look like? Well, neon is going to be 1s2, 2s2, 2p6. That would be neon right there. Okay. So another shortcut way is to say neon with 10 electrons. And then past neon is 3s2, 3p4. That's an abbreviated version. We use the structure of neon as the core, and then we add 3s2, 3p4. Okay? Now that's going to come in handy when you get to something as big as barium. Right? Where's barium? Barium is right over here. It's going to have lots of electrons. And if you draw it out this way, that's not even enough. We got to go beyond that. So if we do, right, there's 4p, right, here's 4p6, and then 5s2, 4d10, 5p6, 6s2. Notice what happens when you get to the third period. That is the N number, principal quantum number. So 3s would be right here, sodium. And 3s2 would be magnesium. Well, if we go over here, there's nothing in there, right? There's no D's, right? So you go straight to 3p's. But then you go to 4s. Now what happens? 4s, 3d. So where are the D's? The D's are right here in the transition metals. 4s, 3d. So whenever you get in this period, in a period, and you get to the transitions, you back up one. Right? Instead of 4, you go to 3. Here would be 5, you go to 4D. Here you got 6S, you go to 5D. Okay? So I hope you're getting a little bit of a taste, an idea of how the table is built. And once you understand how it's arranged and how you step through it, electronically speaking, you can use the periodic table to build your electronic configuration. You don't have to use that diagonal diagram. Okay, so this is the complete structure of barium based upon the diagonal. If you go from barium right here, and you back up here, now you go back up to the next period down here, you have xenon 54. Where is xenon 54? Xenon 54 is all the way up here to 5p6. So another way to write it would be xenon 54, and then beyond that is 6s2. That's barium. Now, what's the advantage there? It goes back to that concept of valency. What electrons are available for reactions? Those electrons that are available for reactions are those that are beyond the noble gas configuration, because noble gases don't react. But if you have electrons beyond the nearest noble gas configuration, those are available for reaction. So in this case, barium has these 2 electrons. Its valence electrons are 2. That's why, and that's characteristic for everything in that group. Barium, strontium, calcium, magnesium, beryllium, they all have s2 electrons available for reaction. That's why they behave similarly. In the first column, those are all S1s, right? 6s1, 5s1, 4, 3, 2s1. Those alkali metals behave the way they do because they only have 1 valence electron. Okay, and the noble gases don't react because they have no valence electrons. Their orbitals are completely filled, right? If that's a 6, that's as many as you can put in there, right? They're filled. They have no valence electrons. Okay, configuration for sodium. Let's see if we can do that one from the periodic table. In fact, I'm going to erase that. So first thing we do is look at sodium. Say, okay, there's sodium, 11 protons. That means 11 electrons. All right, how do we get there? Start with hydrogen, right up here, hydrogen. We're going to do it the long way first. 1s1, 1s2. Then we go down to the second period, 2s2. Then we go across to the p's, 2p6, 6, 7, 8, 9, 10. And then we swing back around to the threes. And the first one we come to is 3s1. That's sodium. If we draw it shorthand, then we take this one. That's neon 10 and 3s1. That's sodium. There we go. And I've already told you this. I stole my own thunder. The electronic arrangement in the outermost shell is the same for elements in the same group. Now, they don't have the same principal quantum number because they're in a different period, but they have the same general arrangement. That's why they're not exactly the same reactivity, but they're very similar. Okay, here's an example. Lithium, sodium, potassium. Right? They're in the same group. Right? Lithium, sodium, potassium. Notice that their outermost shell is S1, S1, S1. That's why they behave similarly. But these are at different energy levels, so they're not exact. They're just similar. And those are the valence electrons. Okay, now that we have an idea of how to structure the electrons in an atom, we can see the arrangement in the periodic table. Which orbitals are being filled as you move from left to right? Well, if you're in this region, right, where you have these two columns, you're filling s orbitals. That's why there are only two columns there, because you can only have 2 electrons in the s. Whereas in the p, you can have 6, right? 1, 2, 3, 4, 5, 6. And the d area, you can have 10 electrons, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's why there are 10 elements across that space, because as you move from left to right, you're filling a d orbital. Now, the one they left out was the f's. Is it on the next page? No, it's not there. All right. The f's are filled. Remember, you can have 7, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3 are the possibilities within the f of the f orbitals. 2 electrons each means 14. So if you look here, you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 elements filling the f orbital. So the lanthanides and the actinides are filling f orbitals. The distinguishing electron, I'm not sure where this is going, but your book mentions it, so I put it in here. The distinguishing electron is the last electron added to the configuration for an element. The last electron causes an element's electron configuration to differ from that of an element immediately preceding it. Well, that's a no-brainer. Obviously, it does. That's why it moves into a different group, because now it's got a different behavior. That distinguishing electron created a new character that it may be similar to others, with distinguishing electrons filling similar orbitals. Okay, columns in the periodic table are known as groups. Elements in groups have similar chemical properties because they contain the same number of outer shell valence electrons. Notice, you may have, if you've had anatomy and physiology, or you've had any other chemistry courses, you may have heard this expression, the octet. The octet is derived from, let's see, bring it back. 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons in these first 2 periods, which is where most of the chemistry that we're interested in happens. So the octet, if it's completely filled, means you have a noble gas configuration, and it's non-reactive. Okay, how do we classify elements? We select their physical properties, metals, nonmetals, right? That determines their physical behavior. Electronic configurations divide the periodic table into regions, right? Regions and groups, actually. Regions, we have the The representative elements are those that are contained in these two columns and these right here, 6 columns. Those are representative elements. These are transition elements here because they transition from one side to the other. These are noble gases. The inner transition elements that they're referring to here are these, actinides and lanthanides. They're in the transition area, but they're inner. And actually, you're filling f orbitals there rather than d orbitals for the rest of the transition elements. Okay. I stole my own thunder. Okay. Elements in group 1 and 2 are referred to as S area elements because those are the orbitals that are being filled. Oh, concept question. That means we're close to the end. I didn't miss it by much. Consider 2 elements. One is a gas. Okay. We got one that's a gas, and the other's a solid. Okay, so they could both be nonmetals, or the solid could be a metal, and the gas could be a nonmetal. That's a possibility. Each contain identical number of electrons in their outer shell. Aha! If they have identical numbers of elements in their outer shell, that means they have to be in the same group. And if they're in the same group, you could still have a metal nonmetal. Why? Because of this stair step right here. So you could have a group here, and you could move vertically. You could go down from a nonmetal and end up in a metal. Okay, so we can't say that they're only nonmetals. These elements are what possibilities could they be? So now we're into test-taking technique, and we need to eliminate the obvious wrong ones. Let's see, one's a gas and one's a solid. So they have to be a gas and a solid together. Okay, so let's see. The first one is fluorine and iodine. That's possible. Fluorine's a gas, iodine's a solid. Okay. How about the number of neutrons? Does that match? Well, let's see. Fluorine is 9 and 19 are possible. So yeah, 10 neutrons, that's possible. How about iodine? 74 neutrons? Well, iodine is 53. And then common 127. Right? So neutrons be 4 and 7. 74 neutrons. Yeah, that's entirely possible. There's a nitrogen is a gas, sulfur's a solid. Oxygen's a gas, sulfur's a solid. Okay, so the first condition is met for all of them. But the second part, if we're eliminating, then we've got our answer. A fits. We could go through the rest of them, but in the interest of time, we've got their answer. How about this one? You're asked to determine the composition of a gas. There are 3 components with 3 different applications. They all have the same atomic number, but the number of neutrons is 0. 3 components with 3 different applications. They all have the same atomic number. same atomic number. Okay. But the number of neutrons is 0, 1, and 2. So this would be Z plus 0, Z plus 1, and Z plus 2. Which element, here's the key, which element has no neutrons in one of its isotopes? The only one is hydrogen. So this would be hydrogen 1, 1, 1. This would be 1 because there's 0 neutrons. This one would be 2, and this one would be 3. Okay. One of the components is used as a radioactive tracer in biological experiments. That's this one, tritium. Identify the gas you were given. So it's going to be hydrogen, isotopes, protium, deuterium, tritium. That's it. The giveaway for me is the fact that they have the same atomic number, but one of them has no neutrons. That was the clincher right there. All right, so we're done with that. Let me stop the share. Okay. Let's see. If there are no questions about the graphing techniques, that exercise if we stay on schedule, that exercise will be due next week. And the laboratory techniques. This is a fairly basic approach just to familiarize everybody with the things that we do in the chemistry lab. So let's see, I think I still have it somewhere here. Where is it? Where is it? Yeah, there it is. Okay, so let me share that one. And it's right here. Okay, expand it some. Yeah, that's good. I had hard copies printed out and ready to give to the class. What you'll have to do is, what you can do is just go into Brightspace and find that lab, and there's the document. You can download the document. You don't have to print it out. You can just study it in your PDF viewer. And then you'll have and then I'll give you a hard copy when you show up next week. That way you won't have to waste your printer. But you do need to look at it, become familiar with it. We look at various things, making measurements, using a gas burner, a Bunsen burner safely, those types of things. I will say that that's probably not the most hazardous, but one of the most hazardous things that you use in a lab is an open flame, because all you need is just something that's needs a little kick, and you can have a catastrophe in your lab pretty quickly. That's why we generally use hot plates now if we need a heat source and we're not in a big hurry, and we don't need high temperature. We'll use a hot plate because it's safer. But sometimes you do need that concentrated heat source. For instance, if we have a substance in a little ceramic crucible and we need to heat it up to a high temperature, you can't do that on a hot plate. You need an open flame. And this tells you how the reaction occurs. And we haven't studied how to write a balanced equation yet, but what you're seeing is methane here, CH4, is reacting with oxygen in the air. And when it does, it gives off a lot of heat. Plus, there's a chemical change. It produces new substances with different identities. You have carbon dioxide and water as the combustion products. Now, if for some reason we restrict the input of oxygen, you get incomplete combustion. In other words, you don't go all the way to carbon dioxide. Some of it may go with carbon dioxide, and some of it may be incomplete and produce just pure carbon or graphite. And we often identify that as soot. The nature of the flame changes also. The color of the flame, the shape of the flame, the structure of the flame changes depending on whether it's properly adjusted for complete combustion or it's restricted and you get incomplete combustion. And there's a description here of that also. That's one of the things that you'll do in the lab. Notice that a properly structured flame has an inner and an outer cone. Well, it says inner, middle, and outer. I guess that's technically true. But what I'm focused on is where's the hottest part of that flame. If it's properly adjusted, the hottest part is right at the tip of that inner blue flame right there. That's where the maximum heat is produced. Now, how to adjust it? Well, it depends. If you have a Bunsen burner with a built-in gas control, it'll be located down here at the bottom. But if you don't have that, then you adjust the gas control from the main valve. Now, the air vent controls the input of oxygen, so it's actually the balance between the two. And it's got slots in it. There are slots in the ring and there are slots in the barrel inside. And when you match those up perfectly, you get maximum air. But if they overlap a little bit and partially closed, you restrict the amount of air that goes into the mixing in the flame. Okay, we're gonna have Pyrex 2. You put that in the flame and see what happens. Then we're going to do some measurements. Right? You need to remember your prefixes. Right? So if you have a meter stick and you're only going to measure something that's about this size, you don't want to report it in meters. Well, you can convert to meters, but the measurement itself will be probably in centimeters. And I think we measure, you can measure your document, right? 8.5 by 11 inches. Well, what is that in centimeters? These are other units of measure that we've determined. We're going to measure mass. So we'll have to have hello? Oh, I picked it up. Should have let her get it. Okay, I'll be right back. Well, actually, I'm Zooming a class. So I was talking to the class. Are you going to? Come on. Come on. All right. When I process this thing, I'll cut that interruption out, so you don't have to sit through that that dead air space. Okay, so we're going to need certain equipment in order to do these measurements. We'll need a meter stick. We'll need graduated cylinders, Erlenmeyer flasks, beakers of certain size. We'll need different types of balances. And I'll talk about those in a minute. We're not gonna need a calorimeter, not yet. Thermometer, yes, we'll need a thermometer. Okay, and that reminds me, I'll need to bring some ice with me. We can boil water, but we don't have a way to make ice. At least not that I know of on the Logan campus. They must keep the ice maker in the executive suites. Then we're going to define and measure things in terms of accuracy and precision, and do our calculations in observing proper significant figures in the calculation. Okay. So first thing you'll notice from a meter stick or a meter ruler is the divisions. Some are big lines and some are small lines. On a, let's see, I got a meter stick here close by. That's not a good one. Let's see. I know I got one, I just can't find it. Let me see if I got a ruler. Here we go. Okay, here's a ruler. And notice it's marked off in with big lines, shorter lines, and then little bitty lines. Okay. The big lines here on this, in this case, are centimeters. So this is 1 centimeter, 2, 3, 4, 5, 6, 7, 8 centimeters. So that means these little lines, and you count how many of them are there between the two. Well, you count, there are 10 of them, 10 lines between the two big lines. That means each of the tiny lines are millimeters. Why? Because a centimeter is 1/100th of a meter, and a millimeter is 1,000th of a meter. So what's the relationship between a centimeter and a millimeter? Well, the relationship between 100th and 1,000th. This is a centimeter. This is a millimeter. Right? So how many of these does it take to make one of those? Well, it's just one decimal place. It takes 10 millimeters to make a centimeter. So each one of those little lines is a millimeter. And remember what I said, what we studied earlier. If your measurement is close to one of these little lines, but not right on it, then your last digit will be an estimate. So you can estimate tenths of millimeters. And that would be your uncertain number or digit, uncertain digit. Okay, if you report this in terms of millimeters, then you would say, oh, right here for A, right? It's between 8 and 9, right? So where is it, 8 and 9? It's 8.123, 8.3, and then halfway between 3, 8.35 would be the estimate right here, so right there. All right. Let's see. We've got calculations here, examples. You can read those. Now, depending upon whether you're doing multiplication, division, or addition, subtraction, remember you've got 2 sets of rules there. One for addition, subtraction, one for add, subtract. In terms of significant figures, be sure you use the right rules when you do those calculations. There's also a discussion here of random error versus systematic error. We haven't talked about that in class. So random error versus systematic error. What's the difference? They are both errors in measurement, obviously. I mean, that's just based upon the name. But systematic errors affects the accuracy of your measure. In other words, a systematic error would be like if you're aiming at the bullseye and you make the same, your error is the same direction and generally area. It's the same error every time. It affects the accuracy of your measurement. Now, actually, that's not a bad thing, because once you know what the systematic error is, you can make corrections for it. And sometimes we do that with thermometers that have a systematic error. Say it reads 2 degrees high all the time. So whenever you make a measurement with that thermometer, you know, because you've calibrated against a standard, you know that it's 2 degrees high. Then every time you make a measurement with that thermometer, you say, instead of 25 degrees, you write down 23, because you know the systematic error makes it high every time. So the systematic errors can be accounted for and corrected for in measurements. Random errors, nope. You never know where a random error is coming from. The random error affects not accuracy, but precision. So if you're aiming at the bullseye and you make a measurement here, here, sometimes over here, sometimes there, it's just a mess. Okay, so this affects precision. This is correctable. This is non-correctable. In the normal sense of thinking of correction. So what we have to do is account for the error some way, so that when we report our values, we can honestly say that based upon random error, this is as good as we can get. So if it's all over the place, we might say our value is 11.4 plus or minus 0.9. So we know it's in there somewhere. We just can't pin it down. And there are statistical ways to handle that, which we don't have time to deal with right now. Okay, so then we get to the procedures. First procedure is the Bunsen burner. So I'm going to show you how to hook it up, how to adjust the flame, and then make some qualitative observations and try to say, with this observation, why did it happen? Okay, and during the lab, I'll be circulating and posing questions and offering advice and so forth and so on. So we don't have to deal with it right now. Just be sure and read the method and understand the steps that you're going to take. Okay, that's the Bunsen burner. Then we're going to use a meter stick to make measurements. This is a description of the meter stick, of course. With your meter stick, we're going to measure the lab manual. Well, we don't have, you might have a lab manual. Yeah, I had you buy one. You can bring it, or you can just measure the handout. That's perfectly acceptable. Make a measurement. In terms of, take the measurement in centimeters to the nearest 0.5 centimeters. Actually, you can probably get more accurate than that. Let's see. Then what do you do? Well, then there are calculations that need to be done. You're gonna know the length and the width of your sheet of paper, say. So what's the area? Well, now you have to multiply those two measurements together. That means significant figures. How many significant figures can you keep in your answer? That's the key to this problem. Then we're going to make some other measurements. Use a graduated cylinder, Erlenmeyer flask, beaker, see which one is more accurate. Okay, how do you read an aqueous solution, or pure water for that matter, in a glass graduated cylinder? All glass, when it comes into contact with the aqueous solution, forms a meniscus. In other words, the top of the liquid is shaped like a bowl. And it looks like this. That's exaggerated, of course. But it looks like that because the attraction between water and the glass is higher than it is for the water and the water inside. So it pulls itself up like that on the water. The other way around, if the attraction is greater inside the material than it is for the material and the container, then it'll go the other direction. And that's what you see with mercury. If you've ever seen a Mercury Barometer, measures air pressure with a column of mercury, you look at the top of the mercury in that column, and it'll be like this. So the convention here, when you take measurements of aqueous solutions in glassware, is you read the bottom of the meniscus. They're calibrated for that type of reading. So you would read across here at the bottom of the meniscus. Okay. Graduated Erlenmeyer flask will have marks on it, but those are pretty crude, right? And the same thing for beakers, are very crude. So you're going to use those. You're going to fill these up to a given mark, depending on what the method calls for, and then pour it into your graduated cylinder and get what we would call the true value. And you compare what you thought you had with the true value. Remember, that comparison is a measure of accuracy. And you're going to say, what's the difference? And on a percentage basis, you ratio the difference between what you thought you had and what you actually have, the difference between those two. You divide that by what you thought you had. So if you think you're measuring 40 milliliters, but the graduated cylinder says you only have 39, then you put 1 divided by 40 times 100. That's your percent error. Laboratory balances, right? We're going to have 3 types. Now, in the method, there's the platform triple beam. And that one is the least accurate. And then we'll have what they call a single pan triple beam. So notice the difference is the platform is all the mechanism is below, and the single pan, all the mechanism is above. This one is supposed to be more accurate. And we don't actually have that arrangement, but I will explain at the time which one is the least accurate, then the next, and then the most accurate is supposed to be the top loading digital balance. So we're going to use those 3 balances to measure the same thing. Let's see, what is it? We're measuring, hold on a second. What are we measuring? Oh, this is descriptive. The measurement part is down here. mass of a quarter. Okay, so bring a quarter to class. Test tube, I'll supply those. Might be a different size test tube, but you just make note of that. And you're in a 125 milliliter Erlenmeyer flask. Right? What is an Erlenmeyer? An Erlenmeyer flask is a flat bottom flask, right? Invented so that you can sit it on the bench top and it won't tip over. There are round bottom flasks that are used in various chemical procedures, but they have to be supported. The graduated cylinder, which means it's got markings on it for volume. Let's see, what else? We're going to measure that, Erlenmeyer flask. This is a nominal value, 125 milliliter. It's actually 125 milliliters up to here somewhere. So the total volume would be more. Let's see, thermometer, we'll measure temperatures and convert, right? So I think we looked at that in class where you convert Celsius to Fahrenheit, or you can convert Fahrenheit to Celsius, convert Celsius to Kelvin. Measure boiling water and a mixture of water and ice. Okay, all right, here's the equipment. Bunsen burner, beakers, flasks, graduated cylinders, meter stick, quarter balances, hot plates. Okay, so we're going to have all of that provided for you. You just need your lab coat and eye protection. And we'll have gloves there if you want to wear them. We're not using any chemicals, so the gloves would provide some protection against getting burned. You can wear the nitrile gloves for that. And we have some pre-lab questions. Let's see. Describe the purpose of the gas control valve and the air vent. These are not quick trick questions, right? They're very simple. Why is a luminous yellow flame often smoky? Right? I mentioned that. Incomplete combustion, and what is going on there? Why is it yellow? Let's see. Which one of these would give you the most accurate measurement for this much salt? Difference between precision and accuracy, you already know that one. Calculate these values, right? You've got different rules, right? You got a subtract rule here. You got a plus and a divide rule, so you got both rules here. Then you got to divide and to multiply. So you have to write the answers with the correct number of significant figures, having rounded them also correctly. Then this is your report sheet. So this is where you put in information that you obtain during the procedure. This is measuring your sheet of paper and the calculations, right? And there are places in here that say, show your calculations. Where is that? It's not there. Okay, this is the first place, right here. Show your calculations. More measurements, percent error, show your calculations. So put your calculations out here somewhere. Which is the most accurate? Measurements of a quarter, test tube, and Erlenmeyer flask on these three different types of balances. Right? And you're going to convert grams to milligrams. So how do you do that? Well, remember, if I haven't said this already, I'll say it again. If the unit of measure gets smaller, then when you convert, the number gets bigger. So if you go from so many grams to a smaller number here for milligrams, you went the wrong direction. So it's a ratio of 1,000 to 1. So if you have 1 gram here, you should have 1,000 milligrams. Move the decimal place 3 places. That's all there is to it. temperature measurements, right? What do you expect to get here? Calculate the Fahrenheit, calculate the Kelvin, and then say something about how well do your readings agree with the accepted values for freezing point and boiling point of water. You know the freezing point is 0 degrees Celsius. Boiling point is 100 degrees Celsius. And express that discrepancy in deviation, you know, plus or minus. What is it? Post-lab questions, all right? So you have to draw some conclusions from your experiment. I already gave you the answer to number 4. Do a measurement, do a calculation here, right? How do you calculate the average value for 3 measurements? Right? That's simple math. Add them together, divide by the number. So if you add these together, what do you get? And then divide by 3. Okay? So let's find the average value. Which one of these matches the known mass of the beaker? Here's the known mass of the beaker right there. Which one of these matches the known mass of the beaker? Which is more precise? In other words, which has the tightest grouping? So the first one has to do with accuracy. The C has to do with precision. Which student has the more reliable balance? Right? That's a judgment call. And it's based upon which one is more accurate and which one is more precise. Okay? Let's see. A student measured the dimensions of a table, recorded these values. According to the student, the area is this. What should the student report for the answer? That's an exercise in significant figures. What should the value be reported? John has a mass of 115 kilograms. Sally has a mass of 115 pounds. Which one is heavier? Right? You can't compare apples and oranges. Kilograms and pounds. That's 2 different units. So you got to convert one of them to the other one to make the comparison. That's why I say show your calculations to justify your answer. Who's heavier? Don't just say 115 pounds is heavier. That doesn't answer the question. Who is heavier? You'd be surprised how many students forget to say that. Sally's heavier, John's heavier, and then prove it. Okay? Mount McKinley in Alaska. I think the name now is different. Used to be Mount McKinley. Now it's Mount Denali. But it's still the same height. Highest peak in North America. That's true. Express the height in meters, in kilometers, to the correct number of significant figures. So how do you do that? Dimensional analysis, right? 20,320 feet. Right? There's where you are. Where are you headed? Well, we're headed to meters. So you need to convert it somehow. If you've got the conversion factor for feet to meters, then you need one conversion factor. But if you don't, then you need to chain them together, right? Convert feet to what? Well, I would convert to inches because I know the conversion of inches to centimeters. And then I can convert inches to centimeters. Then I can convert centimeters to meters, and I'll have my answer. That's the way I would do it. But if you can find a single conversion factor, go ahead on. Just show your work to show meters. Now, how do you convert meters to kilometers? Right? How many meters are there in a kilometer? 1,000. So if your unit of measure is getting bigger, then your number gets smaller. So if you say, I don't know, just for argument's sake, say 7,000 meters. then it would be 7 kilometers. Okay. How about this one? 16.95 gram sample of sugar was added to a glass with a mass of 8.3 ounces. Apples and oranges. What's the combined mass of the glass and the sample in ounces? So if you're going to do that, you convert 16.95 grams to ounces. You need a conversion factor. And then add the ounces together to get this answer. Then you can convert ounces to grams and add them together and get this answer. And then you can convert grams to milligrams because there are 1,000 milligrams in a gram. Okay, so you're going to have 3 answers: ounces, grams, milligrams. And if you would, once you've got your answer, put a box around it or circle or something, because calculations can get messy. And I don't want to have to go searching for your answer, because I might search and find the wrong one, and that would be a tragedy. Okay, that's it. Any questions? All right, so when are we supposed to be? All right, we're finished early, which is not a tragedy.
So we're going to do this lab next Friday, but it won't be due until the following Friday, right?
Exactly right. Yes. As a general rule, lab reports are due the next time we walk into the lab to do a new lab. So that's usually, in the beginning, that's each week. But later on, they stretch out. Some of them stretch out to 2 weeks. I was just checking. I was looking at my schedule. Yeah, if we do all of them, there will be 11 labs. It depends on the weather too. If the weather interferes, we may have to, in order to stay on schedule, we may have to drop a lab or 2. I hope we don't have to do that. Either drop a lab or maybe shift the labs down so that we can get all the first labs in, and we might have to kick one off the end. But that's a decision to be made later. Okay, I guess that's it for today.